Okay, let's jump right into this. If you've ever found yourself wondering how the actual math works under the hood when we try to mimic the brain in silicon, well, you are in the exact right place. We're going to get highly detailed today. We are going step by step through the precise code, the exact mechanisms, and the hardcore calculations behind spiking neural networks. We've got 5 key areas to hit: encoding data into spikes, decoding spikes into predictions, calculating the objective function, solving spatial credit assignment, and finally, taming neural activity. Before we totally zoom into the raw math, let's just trace the high-level blueprint. On the input side, we take continuous real-world data, think raw pixel intensity, and mathematically calculate a conversion into discrete spikes. We then feed those binary signals through our network's hidden layers, and finally, decode that output back into a meaningful prediction. It's all about how we process the global currency of the spike. So, part 1, encoding data into spikes. Biologically speaking, a brighter light might cause your retina to fire more frequently, right? In our networks, we mathematically model this rate code by zooming in on a tiny time interval we'll call delta t. If you make delta t small enough, your exact spike count is bounded to exactly 0 or 1. Repeat that calculation over multiple trials, average those spikes out, and boom, you get a direct probability metric between 0 and 1 that tells you the exact likelihood of a neuron firing in that specific window. So how do we actually calculate this probability in the code? Using a framework like SNN Torch, you'd start by generating a vector of random, continuous inputs. Then, you pass it into the rate-based spike generator function, defining your number of time steps. Under the hood, the engine handles that exact probability calculation, crunching your continuous tensor into a discrete binary tensor of ones and zeros, distributed perfectly across those time steps. But what if you want to save energy? That is where latency coding comes in, relying on the exact timing of a single spike. A biological retina can detect a single photon, or literally millions of them. To handle that massive, wide-ranging stimulus mathematically, we apply a logarithmic compression formula. This calculates a direct conversion from raw input intensity into a specific spike time, meaning a super bright pixel triggers a spike immediately at step 1, while a dark pixel spikes much later, or honestly, not at all. When you swap the programmatic implementation over to a latency function, the algorithm's entire mathematical focus shifts. It fundamentally reprioritizes the precise timing of one single spike over the raw volume of multiple spikes. It's an incredibly elegant way to calculate the exact same input. Our third encoding method is delta modulation. We calculate this by taking a time series input and deriving the exact matrix difference between time steps. Here's the rule. A spike is only generated if that difference is positive and it explicitly crosses a strict, predefined mathematical threshold. Implementing this delta function is just wildly efficient. Imagine a live video feed. Delta modulation literally zeroes out the static backgrounds entirely. If pixels aren't changing, the calculated matrix difference is 0, so no spikes happen. You are exclusively assigning computational power to the exact pixels that change. It is a massive resource saver. All right, moving on to part 2, decoding spikes into predictions. Once we have our spikes, we have to calculate a translation back into a language we can actually measure. Let's compare rate decoding against latency decoding. For a rate-coded output, the math is basically just addition. The network simply sums up the spikes across all time steps for each output neuron, and whichever neuron has the absolute highest spike count becomes your predicted class. But for latency decoding, the network calculates the earliest time to first spike. First neuron to fire takes the win. So why pick one over the other? Well, rate codes offer real mathematical error tolerance. More spikes literally mean stronger, more continuous gradient signals for backpropagation, making your optimization math significantly easier. But latency codes, they are drastically more power efficient, and the math tells us exactly why. A latency code creates a highly sparse matrix. When you're calculating vector matrix products in hardware, an all-zero input vector immediately returns 0. That saves a massive amount of computational energy. Part 3. Calculating the objective function. Now we need to calculate the precise mathematical cost of being wrong. Let's look at cross-entropy versus mean square error for spike counts. With cross-entropy, the network accumulates the total spikes over time and uses those integers as exact logits, which feed directly into a categorical softmax function. By minimizing cross-entropy, the math suppresses the count of incorrect classes. On the flip side, mean square error calculates the sum of square differences between your actual and target firing proportions. So you're mathematically forcing the correct neuron to fire, say, exactly 80% of the time, and the incorrect ones exactly 20%. In a framework like SNN-Torch, all these complex probabilistic calculations get condensed down into highly optimized functions. You just call the specific rate loss function for cross-entropy or mean squared error, and it executes all that underlying math in a single programmatic step. Now, if you are calculating loss for spike timing instead, the math gets a bit trickier. See, cross-entropy inherently wants to maximize the numeric value of the correct class. But in latency coding, a smaller number, meaning an earlier spike time, is actually what we want. To fix this, the calculation requires us to apply a monotonically decreasing function. This cleverly inverts those early spike times into larger numerical logits before they ever hit the softmax function. It's a brilliant little mathematical workaround. Part 4. Solving spatial credit assignment. Biological neurons are essentially one-way streets. They don't do traditional continuous backpropagation. So how exactly do we calculate weight updates? One biologically plausible alternative is perturbation learning, executed in 3 precise steps. Step 1. You add a random noise vector, delta W, to the weights. Step 2. Run the network and explicitly calculate if the output error decreased. Step 3. If the error went down, you accept the new weights. If not, reject them. You have to run massive computational trials to average out the noise, but mathematically, it absolutely works. Take a look at the random feedback approach. Standard backprop scales errors backward using exact symmetric weight matrices from the forward pass, which, again, biology definitely cannot do. Random feedback bypasses this limitation entirely. It substitutes those backward references with fixed random B matrices. The true mathematical marvel here is that replacing a precise piece of the backprop algorithm with random noise still completely allows the network to learn and converge. Finally, Part 5, Taming Neural Activity. To keep things stable, we mathematically apply L1 regularization at the population level. If the total sum of spikes across a layer exceeds our calculated threshold, a penalty hits our loss function, forcing the network to optimize for sparsity. But we can also calculate penalties at the individual neuron level. If a specific neuron falls below a baseline spike count, we penalize the network to effectively force that neuron to fire just enough so that our gradients can keep flowing. But what happens when the exact equations fail you in practice? Well, here is a fantastic secret straight from the developers. If your calculations are causing the dreaded dead neuron problem, where a layer just dies and gradient flow halts entirely, you can bypass complex regularization with a simple programmatic hack. Just explicitly lower the firing threshold parameter of that specific layer. Sometimes a basic parameter tweak is the smartest calculation you can make. I'll leave you with this final thought based on all the math we've unpacked today. Gradient backprop reigns supreme for accuracy, but it completely struggles in biologically plausible scenarios. Since the human brain itself isn't conceptually deep in the same way our 100-layer artificial networks are we fundamentally chasing the wrong calculations by forcing biological learning rules into deep architectures? Maybe the real future of mathematical optimization is figuring out how to make incredibly shallow, spiking networks exponentially smarter. Until next time, keep crunching those numbers.